All right, let's dive right in. Welcome to the Explainer. Today we're taking on chemical reactions. Now, if you've ever looked at chemistry and thought it was just a giant, confusing bowl of alphabet soup, trust me, you aren't alone. But my goal today is to translate all of that into a clear, visual language. We're going to decode the secret messages of the universe and break down exactly how matter transforms. I'm thrilled to have you here, so let's get to it.
Here is our roadmap for today. We'll start by spotting a reaction, and then learn the language of equations. Next, we balance the scales. And finally, we'll look at two very specific types of transformations: combination reactions and decomposition reactions.
So, picture your kitchen for a second. What happens if you accidentally leave a glass of milk out on the counter during the absolute peak of summer? Yeah, we all know the answer. It goes sour, it gets all clumpy, the actual nature and identity of that milk completely changes. And it's not just an annoyance, it's a profound transformation. That is literally chemistry in action.
I love this quote from Martin H. Fisher. "Facts are not science, as the dictionary is not literature. If we just memorize that milk goes sour or that iron rusts, we're basically just reading the dictionary. Today, we aren't doing that. We are going to learn how these facts string together to create the actual literature of the universe. We're learning the grammar of how substances interact."
Section 1. Spotting a reaction, the everyday magic. See, chemical reactions aren't just locked away in labs with people wearing safety goggles and white coats. They're the breathing, the cooking, and the rusting happening constantly, every single second, all around us. But let's look at a really stunning example. Imagine taking a shiny piece of magnesium ribbon. First, you've got to clean it by rubbing it with sandpaper. Then, holding it with tongs, you bring it to a flame. What happens? It doesn't just melt. No, it burns with this dazzling, intense white flame. And when the light fades, that shiny metal is gone, completely replaced by a crumbly white ash called magnesium oxide. It's a dramatic chemical change right before your eyes.
And these dramatic changes prove that chemical reactions leave clues. We don't have to guess if a reaction occurred. The universe actually tells us. There are 4 core visual clues: a change in state, a change in color, a gas evolving, or a shift in temperature. Like if you toss zinc granules into dilute acid, boom, bubbles instantly appear. That's gas evolving. And if you touch the flask, it would actually feel warm, a change in temperature. These are your visual signals that the magic just happened.
Section 2. The language of equations, translating the magic.
Writing all this out in words takes way too long, so chemists developed a highly concise language using word equations and formula. Let's compare a skeletal equation to a balanced one. First, look at the skeletal equation. Mg plus O2 yields MgO. This tells us the pairs, magnesium and oxygen make magnesium oxide. But wait, look closely at the atoms. We've got 2 oxygen atoms on the left, but only 1 on the right. An atom just vanished. That's literally impossible. Skeletal equations are fundamentally unbalanced. They don't reflect reality yet. Below it is the balanced equation. 2Mg plus O2 yields 2MgO. Now the math checks out. We have 2 magnesiums and 2 oxygens perfectly accounted for on both sides.
Section 3. Balancing the scales, the golden rule. This brings us to the absolute climax of writing equations, where we have to step back and apply the strict, non-negotiable rules of the universe. The crucial point here is the law of conservation of mass. You probably remember this one. Mass can't neither be created nor destroyed in a chemical reaction. I want you to picture a physical scale. The total mass of the elements you start with on the left has to perfectly balance what you end up with on the right. You can't just lose an oxygen atom into the void.
So, to satisfy this law, we use what's called the hit and trial method. I know, it sounds a little complex, but let's break it down. It's really like a puzzle. Step 1, draw boxes around your chemical formulas so you remember to never change the formula itself, just the numbers in front. Step 2, list out how many atoms of each element are on the left side versus the right side. Step 3, find the compound with the maximum number of atoms and start balancing right there. Step 4, simply balance the remaining elements one by one.
Let's see this play out with the reaction between iron and water. By following those steps and adding coefficients to the front of our molecules, we reach an equation of 3Fe plus 4H2O yields Fe3O4 plus 4H2. Look at the table. 3 iron atoms on the left, 3 on the right. 8 hydrogen atoms on the left, 8 on the right. 4 oxygens on both sides. We have visually proven that our equation is perfectly balanced on that imaginary universal scale.
Oh, and before we move on, there's one quick trick to making these equations even more informative: physical state symbols. Just a tiny letter in parentheses tells us the state of matter. We've got S for solid, L for liquid, G for gas, and AQ for aqueous, which just means dissolved in water. For example, in that iron and water reaction we just balanced, the water has a little G next to it. That tells us we aren't pouring liquid water on the iron, we're reacting it with steam. It's a tiny detail, but it adds a massive amount of context.
Section 4. Combination reactions, putting together.
A combination reaction is exactly what it sounds like. Two or more substances combine to become one single product. A fantastic example is calcium oxide, also known as quicklime, reacting with water. When you slowly add water to quicklime, they violently combine to form a single new product, slaked lime. But if you were to touch the beaker while this is happening, you'd notice something intense. It gets incredibly hot. A massive amount of heat is released in the process.
And because of that heat release, this reaction gets a special label. This is absolutely crucial to understand: exothermic chemical reactions. These are reactions where heat is released along with the formation of products. The prefix exo means outside, and thermic means heat. Heat is literally exiting the reaction.
What's truly amazing is how personal this is. The energy you're using right now, at this very second, just to focus and watch this explainer, it comes from an exothermic combination reaction. The process of respiration in your cells takes glucose from the food you eat, combines it with the oxygen you breathe, and produces carbon dioxide, water, and importantly, the energy you need to stay alive. You are basically a walking, talking exothermic reaction.
Section 5. Decomposition reactions, breaking apart.
Now, if combination is putting things together, decomposition is the exact opposite. A single reactant breaks down to give simpler products. But a compound usually won't just fall apart on its own. It needs a push. It needs energy. There are three distinct energy triggers we can use here. We can use thermal energy, which means applying heat, like heating limestone. We can use electrolytic energy, so passing electricity through a substance. Or we can even use light, like when white silver chloride powder turns gray just by sitting out in the sunlight.
To see that electrolytic method in action, imagine taking a plastic mug of water, dropping into electrodes, and hooking them up to a 6-volt battery. When you flip that switch on, you are literally shocking the water apart. You'll see bubbles forming right at the electrodes as the liquid water decomposes, splitting completely apart into separate hydrogen and oxygen gases. It's a beautiful, elegant breakdown of a compound.
So we've covered spotting reactions, balancing the scales, putting things together, and breaking them apart. But I want to leave you with one final thought to ponder. We know about combinations and decompositions, but what happens when elements start trading places? What do you think happens if you take a standard iron nail and drop it into a bright blue solution of copper sulfate? Does the iron steal the sulfate? Does the liquid change color? Well, that dips into the wild world of displacement reactions, and that is exactly where we'll pick up next time. Keep observing the everyday magic around you.